Alright, so in the last video, you should have learned about the trends on the periodic table, and before that, you learned a little bit about vectors. Later in this video, we'll apply those. So we're going to take a look at two kids here. We've got this kid right here, who's nice and big. And then we have our smaller friend over to the right. So our big friend is named fluorine, and our little friend is carbon. And in the middle, we have a truck. Now, between our friend fluorine and our friend carbon, who's more likely to be able to get that truck and hold on to it pretty well? Probably fluorine, right? So this applies to electronegativity differences and electronegativity values. So let's recall fluorine's electronegativity value and carbon's electronegativity value. So electronegativity is how much an atom wants to pull the electrons towards that size. And there's a lot of things that factor into this, like the size of the atom, the characteristics of it on the periodic table, how close it is to becoming a noble gas, and if it's metal or non-metal. Dr. Wang should have gone into these a little bit more when he talked about electronegativity differences. We're just going to review them here. So since our friend fluorine is going to be more likely to have a pull on those electrons, this right here is between fluorine and carbon would be a polar covalent bond. Now, a covalent bond, remember, is a bond that's shared between two nonmetals, and polar refers to the electronegativity difference. Now, we have to have a cutoff somewhere, and our cutoff is going to be 0.5. So anything less than 0.5, we're going to consider non-polar covalent. And anything above 0.5 is going to be considered polar covalent. Now, there's one other thing in here that's called ionic bonding. And if we recall from earlier, ionic bonding is a bond that's shared between a metal and a nonmetal. They typically have a very high electronegativity difference because remember, nonmetals are going to typically want to hold on to electrons more than metals are. So they split apart completely when dissolved and create those ions, or aqueous ions most of the time. So let's try one of these out. We have our friend dihydrogen monoxide, or water, over here. So let's first add in the electronegativity values for hydrogen and oxygen. So just after adding those electronegativity values in, we can see that if we subtract 2.1 from 3.5, it's going to give us a value higher than 0.5, indicating that this bond, or the bonds shared, are polar covalent bonds. Now, how do we represent this? We represent this by using the Greek letter delta, which we see right over here. Typically scribbled something along... Ooh, that was a bad one. Let's try that again. Something usually along the lines of that. Now, delta is a typical meaning for a partial charge, right? So remember, these electrons aren't totally getting ripped off and slapped onto the oxygen, but they're just going to trend more towards it. So it creates a partial charge on the oxygen, meaning that because there's more electrons on the oxygen, oxygen is going to have a partial negative charge, and each hydrogen is going to have a partial positive charge. Now there's two more steps that we have to do, and the first one is drawing the dipole arrows. So remember, we're going to represent the pull of the electrons with an arrow, and the arrow is going to start at the positive end and go towards the negative end. And we're going to represent that by putting a little plus sign on the one end of each of them. And then the next step is adding these arrows up to create a net dipole moment. So over on the left, I stuck the two arrows from tip to tail, just like we learned. And the net dipole moment of this guy of oxygen is going to be straight up, just like that.